Pi is for sure one of the most fascinating numbers of mathematics. It appears in geometry, calculus, quantum physics, and various other fields. There are many features that make pi a very special number, but today we will focus on one: irrationality. Rational numbers can be written as a fraction of two integer numbers. But already at the times of ancient Greece, the philosophers knew that there are numbers which cannot be written as such a fraction of integers. Those numbers are called irrational, and Euclid found a proof for the irrationality of the square root of 2. But let's go back to pi. Looking at the decimals of pi, it's quite obvious that there cannot be a pattern, so pi cannot be a rational number. But just looking at the decimals and not finding any recognizable pattern is not a proof. The first mathematician who was able to prove that pi is irrational was Johann Lambert in the 1760s. About 200 years later, Charles Hermite found a simpler proof, making use of only basic calculus. Probably he was annoyed by the lacking abilities of his students. But even Hermite's proof can be simplified, and one guy who did this was Even Neven, and his proof is the topic of this video. So, let's go! So the proof, like many other proofs in mathematics, starts with assuming the contrary. So we go by contradiction. We assume that, let's make that not so thick. So we assume that pi is a rational number, and a and b are integer numbers. So we can write pi as the fraction of two integer numbers. This is the first step of the proof. Now we need to do some preparations before we can go to the actual steps, but those preparations will be quite short. So Even Neven defined two functions. The first function he defined was f of x, small f of x, being x to the power of n times a minus b times x, and then close the brackets, to the power of n divided by the faculty of n. And n is an arbitrary natural number, and this number is going to be very important later in the proof because this will help us to actually conclude our contradiction. So n is an arbitrary natural number, and you can see that we have a and b here, so we have the integers that form our fraction, that is pi. So we see that pi is a part of this function. And the second function that Even Neven defined is based on this small f of x. So we have capital F of x is equal to small f of x minus the second derivative of f of x plus the fourth derivative of f, and so on up until the 2nth derivative of f. So this is the second function he defined. Now we have done all the preparations we need. So let's take a look at the steps that we're gonna go through. The proof itself is based on 3 steps. So the first step is we're going to prove that f of 0 and f of pi are both integers. Then in the second proof, in the second step, we're going to take a look at the integral from 0 to pi over f of x, so the small f of x, times sine of x dx, and we're going to prove that this integral is equal to f of 0 plus f of pi, and therefore is an integer. And in the third and final step, we're going to show that this integral will become very small for very large n, for very large arbitrary n. And this will be our contradiction. Show that the integral, so let's copy that, is smaller than 1 for arbitrary large n. So let's start with step number 1. Step number 1, f of 0 and f of pi being integer numbers. So we start with f of 0. F of 0 is small f of 0 plus the second derivative at 0. No, that is not a plus, that is a minus. Here's the plus, the fourth derivative of 0, and so on up to the 2nth derivative at 0. So what we're going to do now is we're going to take a look at how those derivatives look like evaluated at the point 0. So first of all, f of 0 is quite obvious because we have our function here, x to the power of n times the brackets, and we see that x is 0, so 0 to the power of n is 0, so we have a 0 in the numerator, so the whole thing gives us 0. But it's getting a bit more interesting when we're going to take a look at the derivatives, at the even derivatives. So first of all, let's think about how the function f of x would look like if we would expand it with the binomial theorem, because we have f of x being x to the power of n times a minus bx to the power of n divided by n faculty. So let's not think about the coefficients specifically, but more like what type of numbers there are. So we know that a and b are integer numbers, and we just want to know the coefficients of the axis to the power of between n and 2n. So this whole thing will be the sum over k starting at n going to 2n of ck divided by n faculty times x to the power of k. So this is how our function f looks like, and we know that ck is an integer. So this is what we need now to take a look at the even derivatives, because if we take the derivative, the kth derivative of this function here, then we will get that fk at the point 0 is equal to ck divided by n faculty, and then from all those k derivatives that we take of a polynomial x to the power of k, we get k faculty. And this whole thing indeed is an integer. So we know that f of 0 is 0, and we know that each derivative of this function is an integer. So we know that the sum of those functions is an integer as well. So this is our conclusion. F of 0 is an integer. So let's go on to f of pi. And to understand how we can prove that f of pi is also an integer, we have to take a look at the function small f evaluated at pi minus x. So let's plug that in. We know that f of x is this whole thing here, so let's copy that down here so we can see it. Ba-bum. So we have f of pi minus x. So let's plug that in. We have pi minus x to the power of n times a minus b times pi minus x, and close the brackets, to the power of n divided by n faculty. All right, so let's go. Pi is a divided by b, so this is how we define pi, as a fraction of two integers. So we have a divided by b minus x. Yes, I was confused for a second by my own thoughts. So a divided by b minus x, this is our fraction of pi to the power of n, and then times a minus bp minus bx, and the whole thing to the power of n divided by n faculty. And this bp we can exchange for b times a divided by b, so the b's, they cancel each other out, as we can see here. So we can continue to write that this is a divided by b minus x to the power of n. Then we have here a minus a, so this is 0. So we stay with, here this has to be a plus because minus on minus. And we are left with bx to the power of n divided by n faculty. And now we can drag the b to the power of n in here. So we will get that a minus b x in brackets to the power of n times x to the power of n divided by n faculty, and this is just f of x. So what we've just shown is that f of pi minus x is equal to f of x. And this will help us to find out what the derivatives of the small f of x look like evaluated at the point pi. So let's take a look at the first derivative of f of pi minus x. So we have d of dx f of pi minus x would be, if we use the chain rule, minus the first derivative of f. So what we can write now is that the kth derivative of pi minus x is probably, or most probably, most definitely, minus 1 to the power of k times f, sorry, not f of x, but the kth derivative of x. So if we now say x is 0, if we set x to 0, we get f of k, the kth derivative of f evaluated at pi is minus 1 to the power of k times the kth derivative of f evaluated at 0. And this is definitely an integer, so we know now that the kth derivative of f evaluated at pi is an integer as well, and from this we can conclude that capital F function is also an integer if you evaluate it at pi. So now we have finished the first step, and we can continue with the second step, taking a look at the integral and showing that the integral is an integer. So second step, we're going to take a look at the integral from 0 to pi over f of x times sine of x dx, and we are going to show that this is equal to f of pi plus f of 0. So first of all, we're starting by looking at the second derivative of the capital F function. So the second derivative of the capital F function is the second derivative of the small f minus the fourth derivative of the small f, and so on, and we keep on going up to minus n to the power of k f to the power of 2n of x plus, let's write that here, minus 1 to the power of k plus 1, and the 2nth plus 2 derivative. So what we know is that the degree of our function small f is 2n. So from this we can conclude that the 2nth plus 2 derivative of x is 0. And now we can just add the second derivative of x to just capital F of x, and then we will get that this is just small f of x. So this we can use now to take a look at the integral. So what we're going to do is we just multiply this equation with sine of x. So we have f, the second derivative of capital F of x times sine of x plus capital F of x times sine of x, and this is equal to f of x times sine of x. So what we're going to do now is we're going to transform that whole side of the equation into the derivative of one term. So derivative of one term, of one sum to be more precise, and we're going to do that by using the product rule in reverse. So let's take a look at f, this first term here, f, the second derivative of capital F times sine of x. So if we say that this looks like the product rule has been applied, then it looks like f derivative of x times sine of x, and then taking the derivative of that would give us the second derivative of x times sine of x, and now I have to make that a bit smaller, plus the first derivative times cosine of x. So if we rearrange that equation with respect to the second derivative of capital F, we will get that the second derivative of capital F of x times sine of x is equal to this first derivative of x times sine of x, and then in brackets we take the derivative minus f derivative x cosine of x. And now we do the same thing with the second term, f of x times sine of x. So f of x times sine of x. This looks a lot like we could use the sine of x as the function that has already been taken the derivative of. So what we could say is that, let's put that down here, that minus f of x cosine of x derivative is equal to minus f derivative of x cosine of x, and then take the derivative of cosine, which is minus sine, so we get plus f of x times sine of x. So from this we will get, or let's write that just up here, that this is minus f of x cosine of x and the whole thing derivative plus the derivative of f of x times cosine of x. And as you can see, we have minus the derivative of f times cosine of x, and we have plus the derivative of f times cosine of x. So those two terms, they cancel each other out. So what we get in the end, that is that the second derivative of capital F of x times sine of x plus f of x times sine of x is equal to, so let's take this term here, or let's do it in another color. So this is equal to first derivative of x times sine x, take the derivative, minus this term here. So f of x cosine of x derivative. So this means we can just use the sum rule, and we can say that we take the derivative of the sum of those two functions. So we have the derivative of f times sine minus f times cosine and the whole thing primed. All right, so we know that this is f of x times sine of x. And from this we can conclude that this function here is a solution to the integral. So the integral from 0 to pi over f of x times sine of x I'm sorry, I had to drink a little sip. All right, the integral from 0 to pi f of x sine of x dx is equal to f of pi times sine of pi minus, f prime of pi minus f of pi cosine of pi minus f prime of 0 sine of 0 plus f of 0 times cosine of 0. And this sine of pi is 0, sine of 0 is 0, cosine of pi is minus 1, and cosine of 0 is 1. So we get in the end that this is f of 0 plus f of pi. And therefore, this integral is an integer. So we know that this integral is an integer, and this is completely based on the assumption that pi is a rational number, that pi can be written as the fraction of the two integers a and b. What we're going to do now is we're going to show that this integral actually is smaller than 1 because we can choose this n in the function arbitrarily large. So let's take a look at how exactly this goes. So third step is our conclusion. So let's take again a look at the integral from 0 to pi f of x times sine of x dx is equal to, now let's plug in our definition of the function, so we have x to the power of n times a minus bx to the power of n divided by n faculty times sine of x dx. And now what we're going to do is we're going to estimate an upper bound for that integral, and we will find out that an upper bound for that integral is 1 actually. So the integral is smaller than 1 for arbitrarily large n. So how do we estimate that upper bound? Let's take a look at x times a minus bx. So we know that from the integral limits, it goes from 0 to pi, we know that x is in between 0 and pi. So we can write 0 is smaller than x is smaller than pi. Therefore, this whole thing here is smaller than pi times a minus bx. And now we can also conclude that if we put that term away, then we will also get that this is smaller than pi times a. Therefore, we can say that x to the power of n times a minus bx to the power of n divided by n faculty is smaller than pi a to the power of n divided by n faculty. Now, the second thing that we know is because x is in between 0 and pi, we know therefore that sine of x is in between 0 and 1. So this means that sine of x is smaller than 1, which therefore means that the whole integrand f of x times sine of x is smaller than the constant pi a to the power of n divided by n faculty times 1 from the sine. This means that the integral from 0 to pi of f of x sine of x dx is smaller than pi a to the power of n divided by n faculty. We can extract that out of the integral because it is a constant, it's not dependent on x anymore, times the integral from 0 to pi dx. This integral just gives us pi, so the whole thing is pi times pi a to the power of n divided by n. So we know now that the integral from 0 to pi of f of x sine of x dx is smaller than pi times pi a to the power of n divided by n faculty. And this n is arbitrarily large. And for arbitrarily large n, this whole term will be smaller than 1. And therefore we have our contradiction. Because first we've shown that under the condition that pi is a rational number, this integral is an integer, but then we have also shown that this integral actually with a defined function can become smaller than 1 and thus cannot be an integer at all times, and this is our contradiction. So if you like this video, please leave a like, subscribe to the channel if you haven't done that already, leave a comment. I like to talk with you people, and yeah, thanks for clicking on the videos. Thanks for staying with me until now. Man, I'm nervous. I'm sorry. All right, so was cool, and see you in the next video. Bye.